In this chapter, we're going to take a very high-level overview of Pig and look at many of the basics around it, such as its architecture, how it uses data structures, and the data structures that it does use, the data bags, tuples, atoms, and maps. We'll look at each of those in detail. We'll look at the for each generate statement, which is very useful to iterate over embedded values in an individual record. And we'll take a look at a sample query and walk through exactly what's going on. First up, the Pig architecture. We see here in the upper right, we have our cluster, and in the lower left, we have our orange client, and in the upper left, we have our centralized server where we've been installing services like Hive and the Metastore and so forth. The Pig client can install on each individual client. This client can then be configured for the location of the job tracker, and when we run a Pig Latin script on the client will submit it directly into the job tracker. This, again, is probably maybe not the preferred way to set up Pig in a modern environment. A better way is to probably use a Pig server or Hue. This works the same way that the Hive service worked, where we have a centralized server and we set this product up for web browser access to be able to submit Pig queries via a web browser. The Hue web interface and third-party tools like TalentD and Qubole offer a way to set up Pig as an independent server. Now, when a client submits a query, they typically open a web browser and submit the query into that machine. And that machine is configured only once with the location of the job tracker. And the Pig server will then take the user queries, compile them into pre-built binaries, run a series of MapReduce jobs in the cluster, and then report the results back to the user. Again, the nice thing of using something like this, as we saw with Hive, is that we can have many clients. None of them need individual config to the job tracker. All they need is a web browser to be able to access this Pig server or Hue service. Again, Pig uses absolutely no Metastore, whether it's installed as a server or on each individual client. The Pig Latin queries do a schema on read or a data load at the top of each of the individual script so that the user actually lays out specifically which HDFS directories they want to work on. So again, Pig works very much as we saw with Hive. It simply chains together pre-built binaries into an execution path to run MapReduce jobs that perform the query or perform the processing that's required. Again, just like Hive, we cannot get the Java source to build from or optimize against. And again, this is exactly how Hive works. Really, the big differences are in the interface that each exposes. So one of the big differences with Pig is it uses this concept of data bags, tuples, atoms, and maps. An atom, which we're designating in our query here, or in our results going forward, is a single quote. And again, you can think of this as a single scalar value, the same way that you have Java primitives or primitives in other languages. Although here we're saying that these primitives are like Java primitives, each atom is a string. So each atom is not an individual integer or double and so forth. Some examples here would be the string rich or the number 1.9. Again, all these are represented as strings. Next up, we have tuples, which we're designating a tuple via any data in between angle brackets. This is an ordered sequence of fields, and a field can be of any type. A field could be an atom, a tuple, or a data bag, so tuples can incestually contain other tuples. You want to think of tuples the same way as you think of a row in a database paradigm. An example of a tuple here is we're saying this tuple T is equal to, again, we're designating a tuple, the number 5 in the first ordered sequence of field. The next thing in here is actually a data bag designated by a braces, and inside that data bag we have several tuples. And then the third tuple is actually a map type, which we'll discuss here in a bit. And then we see the end of the tuple designator. Second to last up, we have data bags, which we're designating via curly braces. Data bags contain a set of tuples, and every tuple needs to be the same. Here you want to think of a table or set of rows in the database paradigm is equal to an entire data bag. An example here would be, again, we have these curly braces designating a data bag, and inside of here we have a set of tuples. This first field is a single atom, which is a string, and the second field looks like is an IP address. And again, we have the end of the data bag designator. Last up, we have maps, which contain key value pairs, and you can think of these as an associative array or a Java hash map, where the value part of the key value pair can be of any type. Could be an atom, could be a tuple, could be a data bag, or it could be another map. And an example here would be something like a clearance field has the value of top secret, and we could include this map as, again, part of another tuple. So now let's look at a sample query. Here we see at the top, we are loading this prods directory as a category and inventory. Again, this prods is a directory that exists. In this case, it's a directory relative to this user's home directory, the user who's running this script. We could also specify a fully qualified path to a directory in HDFS. But we're essentially loading all of the data in all of these files into this product data bag. And inside that product data bag, we'll have sets of category and inventory. Next up, we run a filter operation. Filter essentially lets us take out certain rows and run a filter to make sure that only certain rows make it past this. Here we're saying that anything that has an inventory greater than 0 is allowed into this filter. So we're going to put products by cat. All the data that contains an inventory greater than 0 will be put into this products by cat table. We're now going to run a second filter operation, which is going to count up the number of products in each individual category, and any category that has over 1,000 products in it is going to make it past this filter. We're calling this data bag major categories. Now we're running a for each generate statement. We're saying that for each major category, we're going to generate not only the category name, but the average of the number of products contained in that category. We'll look at this for each generate statement in detail in the next slide. And finally, at the very end of a query, we have either a dump or a store statement. With the Pig Latin script, it essentially just starts processing syntax, and it keeps going through and saying, okay, that's valid syntax, okay, that's valid syntax. When we finally hit either a dump statement or a store statement, we then submit this query into the MapReduce cluster. In the case of dump, it simply dumps the contents of this data bag back out to the terminal. In the case of a store statement, we would then store this data back into HDFS. Again, you can see here that the syntax contains data flow statements like count, filter, and so on. It's also mixed with standard programming syntax such as for each statements. It might be a little bit harder to wrap your head around than SQL statements, as we saw with HiveQL, but we can see that this offers a bit more richness and variety in how we can process our data. Minus the load and dump statements that we have at the top and the end of the script, it roughly equates to the same amount of lines that we had in the HiveQL statement, which we see in the Hive Basics deck. This isn't always the case. Typically, Pig will result in more lines of code, but for smaller queries, the number of lines are roughly equivalent. Let's zoom in now on this for each generate statement. Here we saw the for each major categories generating the category and the average of the products.inventory. A for each and generate can iterate over the tuples, pulling out only specific fields. Aggregator operations like average, count, minimum, max, and so forth can be used on these embedded structures. And as we see here with the products, we're getting the average of the number of products inventory across every category. This is a very useful thing to do in Pig. Again, this was a very high-level overview of Pig Basics, but I strongly recommend the book Programming Pig by Alan Gates, as well as this URL right here. And let's actually all go ahead and click on this URL and walk through the Pig documentation. Here we see some Pig Latin basics. This is a great place to go through and learn more about the comparison operators and also see some actual examples that we could run in our Pig interpreter. Our labs will actually use some of these statements, but you can always come back in here and run more.